Welcome to All Force e-learning. Yesterday we have discussed about Markovnikov rule, nothing but addition of electrophiles or nucleophiles to alkene system. So already we have discussed that Markovnikov rule is applicable for only unsymmetric molecules but not symmetric molecules. Now we will see example here. For example, here ethylene molecule or whatever double bonded compound is given, these molecules undergoes electrophilic addition reactions. Here HCl is given or whatever compound is given. First step is electrophile attacking step here. That means electrophile attacking step E plus. So E is added to the double bonded carbon here. Now C here electrophile. So here positive charge. After attacking of electrophile to unsaturated system, form the carbocation intermediate. Not only this reaction, whatever reaction is given, if reaction proceed via carbocation intermediate, then rearrangement is possible. Again, the positive carbon which is having plus, having how many sigma bonds? 1, 2, 3. 3 sigma bonds means carbocation hybridization state is sp2. So here rearrangement is possible here. Next step is nucleophile attacking step. Here electrophile, here nucleophile here. This is the way to write the mechanism of electrophilic addition reactions. For example, here propene molecule is given. Propene molecule is given. Addition of HCl to propene molecule. Which is electrophile in HCl? HCl, H plus and Cl minus. Cl minus is nucleophile, H plus is electrophile. Given system is unsymmetric system. Here methyl group is there, here there is no methyl group. Which is having more number of hydrogens? This one. Which is having less number of hydrogens? This one. Markovnikov rule is applicable for this molecule. According to Markovnikov rule, the nucleophile is added to more substituted carbon which is having less number of hydrogens. According to Markovnikov rule, electrophile is added to a less substituted carbon which is having more number of hydrogens. That means here CH3 again CH. Cl is added to middle carbon. Reason, more substituted carbon, more stable intermediate is formed if you write that mechanism. Again, electrophile is added to CH2 group. For example, HBr is given. H plus electrophile, Br minus is nucleophile. Again, CH3 group here, CH2. The Br minus is added to more substituted carbon, here Br, here H. Supposed to be Hi is given. Hydrogen iodide is given. Which is electrophile? H plus, I minus is nucleophile. Again, Markovnikov rule. I minus is added to second carbon, which is having more number of bonds here. Here CH3 group, again CHI, here CH2, H is given. This is the way to write that electrophilic addition reactions. Supposed to be here HBr is given, R2O2 is given, R2O2, whatever peroxide is given, doesn't matter here. Wherever peroxide is given, the reactions follows free radical mechanism but not electrophilic addition mechanism. So, peroxide is given free radical mechanism and form the anti-Markovnikov product but not Markovnikov product. Anti-Markovnikov product means we have to add the reverse in this case. Br minus is added to less substituted carbon which is having more number of hydrogens, and H plus is added to more substituted carbon. Reason, secondary free radical is more stable than primary. If you write the free radical stability order according to inductive Merrick effect or mesomeric effect, whatever effect is given doesn't matter. If you apply the principle, stability order is tertiary free radicals are more stable than secondary, secondary is more stable than primary. According to that concept, the reaction proceed via free radical mechanism. Stable free radical intermediate is important in this case. For example here, here CH3 is given, again CH. So HAr CH2Br in this case. Anti-Markovnikov product is formed here. The effect is generally called peroxide effect or Karash effect. So that effect is generally called what? Peroxide effect. Peroxide effect or Karash effect. Karash effect. So peroxide effect or Karash effect here. Peroxide effect or Karash effect is applicable for only HBr addition but not HF, HCl and HI. In the presence of peroxide also, HCl addition and HI addition form the Markovnikov products but not anti-Markovnikov products. Reason, HF is given, HCl is given. HF is given, HCl is given, HBr is given, again HI is given. According to polarity, that means according to bond nature, electronegativity difference is more. Here also same thing, electronegativity difference is more. Even the peroxide is given that both molecules undergoes heterolytic cleavage but not homolytic cleavage. Homolytic cleavage is possible means form the free radicals. Equal distribution of electrons. Whatever the bond is given, the bond is carrying 2 electrons. Equal distribution of electrons means form the odd number of electrons, nothing but free radicals. Here HF, HCl molecules undergoes heterolytic cleavage but not homolytic cleavage. Due to that reason, peroxide is given or not doesn't matter. Form the Markovnikov product. Wherever HBr is given, somewhat electronegativity difference is less in between the H and Br. Due to that reason, in the presence of peroxide, the bond undergoes homolytic cleavage, form the free radicals. So the reaction proceed via free radical mechanism, form the anti-Markovnikov product. Wherever HI is given, HI also possible but here, but iodine reducing properties are more and dimerization power is more here. Due to that reason, HI also follow that Markovnikov rule but not anti-Markovnikov rule even though peroxide is given. This is a way to explain the peroxide effect or Karash effect. Finally, the peroxide effect is applicable for only hydrogen bromide addition reactions but not HCl and HI addition reactions. For example, here symmetric molecule is given For example, here CS2 is given, here HCl is given, HBr is given, whatever hydrogen iodide or hydrogen fluoride is given. Addition reactions CH2 again CH2Cl. Here CH2, here CH2Br. Right side addition or left side addition doesn't matter. Given system is symmetric system. Symmetric system is given, need not to follow that Markovnikov rule. Markovnikov rule. Wherever unsymmetric system is given, we follow that Markovnikov rule. Even though peroxide is given, right side addition or left side addition will get same type of product. So the Markovnikov rule is not applicable for symmetric molecules. Symmetric molecules here. Symmetric molecules here. For example, here compound is given like this, which is having double bond here, double bond. Addition is hydrogen chloride addition, HCl addition. So reactant is carrying double bond. Double bond is given, electrophilic addition reaction is possible here. Electrophilic addition reactions. So here number of hydrogens 2, number of hydrogens 1 here, number of hydrogens 2 here. Here only one hydrogen. Given system is unsymmetric system. Then electrophile is added to less substituted carbon. Less substituted carbon here. So here less substituted carbon. Here CH2H. CH2H here. Now C plus is formed in this case. C plus. Wherever this type of intermediate is formed, ring expansion is possible. Ring expansion is possible. Why we have to write the ring expansion product means, based on the stability of cycloalkanes we can explain. If you write the stability of cycloalkanes, cyclohexane is more stable when compared to cyclopentane. Cyclopentane is more stable when compared to cyclobutane. Cyclobutane is more stable when compared to cyclopropane. Based on the Bayer-Stein theory, we can explain that concept here. So, how can you identify ring expansion is possible or not? Means, if ring connected carbon is carrying positive charge, then only ring expansion is possible here. Ring expansion is possible. Supposed to be, if you give the numbering, here 1, here 2, here 3, here 4, here 5, here 6. Here 6. Fifth carbon, first carbon, sigma bonded electrons migrate towards sixth carbon. Reason, electron deficiency is there. Or second carbon, first carbon, sigma bond electrons migrate towards C plus or sixth carbon. Supposed to be, if we take this one, whenever the sigma bond electron migrate towards C plus, new sigma bond is formed in between the C5 and the C6. New sigma bond is formed in between C5 and C6, which is going to lose the electrons here, first carbon. Then the first carbon gains positive charge. Positive charge. So now, how many member ring is formed here? 6 member ring. 6 member ring. If you give the numbering 1, 2, 3, 4, 5, 6. The sixth carbon is having methyl group. Methyl group. The sixth carbon is having methyl group, which is having positive charge right now. First carbon. Reason, the first carbon is going to lose the electrons in this case. So, first carbon. The formed carbocation is secondary carbocation. Here, CC bond means secondary carbocation. Here tertiary carbon is there. Tertiary carbon. Less stable carbocation convert into more stable carbocation. Wagoner, Mervian rearrangement is generally called what? The type of rearrangements are called Wagoner, Mervian rearrangements. So reason tertiary carbocation stability is more when compared to secondary. Secondary is more when compared to primary. In this way, the hydrogen migrate towards first one, then form the more stable intermediate. C plus. More stable intermediate is formed here. Tertiary carbocation. Final step is nucleophile attacking step. Which is nucleophile here? Cl minus. Which is electrophile? H plus. Here HCl is given, the bond undergoes heterolytic cleavage. Always sigma bonded electrons migrate towards more electronegative atom. So Cl minus H plus. Final step is nucleophile attacking step. The nucleophile is added to C plus. Then form the compound like this. Here CH3Cl. CH3Cl. According to numbering, the first priority is given to Cl. 1, 2, 3, 4, 5, 6. 1 chloro, 1 methyl cyclohexane is formed here. 1 chloro, 1 methyl cyclohexane is formed here. This is the way to write the ring expansion reactions. If you take methyl, extra methyl group is there here. This is the way to write that final product here. Final product. So these type of reactions are electrophilic addition reactions. If you take alkene system, here C double bond CH2 is given, ethylene molecule is given. Ethylene molecule undergoes addition reactions with X2 in the presence of carbon tetrachloride medium. Carbon tetrachloride medium here. X2 in the presence of carbon tetrachloride medium here. So nothing but addition of halogens to alkene system. Addition of halogens to alkene system. But the reaction proceed via cyclic intermediate but not carbocation intermediate here. So here X is given. Here CH2, again CH2. Here X, again X. Here also same thing. In between the two X, one sigma bond is there. That sigma bond undergoes heterolytic cleavage but not homolytic cleavage. First step is electrophilic addition step. After formation of intermediate, after formation of less stable intermediate, by using halogen lone pairs form the cyclic intermediate. Based on the mechanism we can explain this one. So final step is trans addition step. Nothing but halogenation addition reactions are trans addition reactions. For example, here CH3 is given, here CH double bond, here CH2 is given. Propene molecule is given. Propene molecule reacts with chlorine in the presence of carbon tetrachloride medium. Addition is trans addition. Here CH3, again here CH, again CH2, Cl. Addition is trans addition here. Final product is 1,2-dichloropropane. 1,2-dichloropropane here. 1,2-dichloropropane. Based on the given reactant, we can explain stereochemistry of products. Here. For example, here CH3 is given, CH3 is given, CH double bond, again CH3 is given. Given compound is trans compound. Given compound is trans compound. So trans butene, 2-butene compound. Here Br2 carbon tetrachloride is given. Medium is carbon tetrachloride medium. Given compound trans compound, addition is trans addition, then form the meso compound. That means here trans plus trans reactant, trans addition, then form the meso compound. For example, here trans reactant is given, addition is cis addition. Addition is cis addition. Form the racemic mixture. Reactant is cis reactant. Addition is trans addition. Opposite addition. Then form the racemic mixture. Here trans is given, cis reactant is given, addition is cis addition. Then form the meso compound. Based on these principles, we can write the product directly. So here given reagent, trans addition reagent, reactant trans plus trans, then form the meso. Here CH3 group, here CH3 group, here Br again, Br. Meso compound. Due to the presence of planar symmetry, compound is generally called what? Meso compound. Optically inactive compound is formed. The type of compound is called what? Meso compound. If you follow these rules, we can write the final product wherever stereochemistry is given. If they do not given stereochemistry, means we can write the product directly transition product. Given product, formed product is trans compound or cis compound, doesn't matter. Wherever stereochemistry is given, then we have to follow the stereochemistry only. For example, here cyclopentene is given. Cyclopentene is given means here Cl2 or Br2. Here carbon tetrachloride medium. Given reactant is cyclopentene. The reactant is carrying double bond. Again, addition is trans addition. So form the product like this. Here Br, again here Br. Trans product is formed here. Trans 1,2-dibromo cyclopentane. This is the way to write the products. Nothing but addition of halogens to alkene system. That means addition reactions are trans addition reaction. Intermediate is cyclic intermediate. You remember, not carbocation intermediate. The reaction proceed via more stable intermediate always. So this is the way to write the products from alkenes. Now preparation of halogens from allylic compounds. Nothing but allylic halogenation reactions. Allylic halogenation reactions. Allylic halogenation reactions means the reactions proceed in the presence of high temperature here. So how to identify the given compound is carrying allylic carbon or not? Already I told you yesterday class, C double bond C. The carbon is generally called what? allylic carbon. Here also allylic carbon. Here also allylic carbon like this. Which is connected with double bonded carbon is called allylic carbon. The allylic hydrogen is replaced by halogens, chlorine or bromine, iodine. This type of reactions are generally called allylic halogenation reactions. Allylic halogenation reactions. But we have to apply the suitable conditions in these reactions. Under normal conditions, allylic halogenation is not possible. Reason, the reactant is carrying double bond. Then addition reaction is possible. Then how to prevent that one? We need only allylic halogenation, means we have to apply these some conditions. Conditions N-bromosuccinamide, NBS, N-bromosuccinamide, 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 N-chlorosuccinamide, N-chlorosuccinamide, high temperature, 500 degrees centigrade temperature or 773 Kelvin temperature. High temperature 773 Kelvin temperature or SO2Cl2. Again we have to apply the high temperature. Here. So if you apply these conditions, we can get allylic halogenation. Here. Here also same thing. Tertiary allylic hydrogens are more reactive when compared to secondary. Secondary is more reactive when compared to primary compounds. If you write the reactivity here, tertiary allylic hydrogens are more reactive than secondary. Secondary allylic hydrogens are more reactive than primary compounds. Reason, tertiary is given the reaction proceed via more stable intermediate. So according to that stability order, tertiary is more stable than secondary, secondary is more stable than primary compounds. For example here, propene molecule is given. The propene molecule is carrying how many allylic hydrogens? How many allylic hydrogens means how to identify that one? The carbon must be connected with double bonded carbon. This one is allylic carbon. The allylic carbon is having how many hydrogens? 3 hydrogens. So compound reacts with Cl2 in the presence of 500 degrees centigrade temperature. Allylic halogenation is possible. H is replaced by Cl. Allylic hydrogen is replaced by chlorine. Final product is CH2 double bond CH2Cl here. CH2Cl. 3-chloropropene is formed here. According to IUPAC nomenclature rules, the first priority is given to function. So 3-chloropropene or allyl chloride. Allyl chloride is formed here. Allyl chloride. For example here, CH2 double bond. Here CH is given. Here CH2 again. CH double bond again. CH3 is given. How many allylic carbons? 2 allylic carbons. 1, 2. How many allylic hydrogens? 5 allylic hydrogens. 3 plus 2, 5. What type of allylic hydrogens? Secondary, primary. How can you identify given hydrogen is primary or not? CC bond means primary. 2 CC bonds means secondary. Based on the connectivity, we can identify given carbon is primary or secondary or tertiary. So secondary carbon is having hydrogens, secondary allylic hydrogens, primary allylic hydrogens. Which one is more reactive towards allylic halogenation? Which one is more reactive towards allylic halogenation? Secondary is more reactive when compared to primary. So again, if you take chlorine in the presence of 500 degree centigrade temperature. So here CH3 is given, again CHCl, CH double bond, again CH3 is formed here. CH3 is formed here. This is the way to write that product. For example, cyclohexene is given, cyclopentene is given, cyclopentene, N-bromosuccinimide is given, N-bromosuccinimide, the given reactant is having how many allylic carbons? 2 allylic carbon. Carbon connected with double bonded carbon. Carbon connected with double bonded carbon here. So both are having same nature. If you replace that hydrogen here or here, doesn't matter. That means here bromine or addition of bromine here doesn't matter here. So bromocyclopentane is formed here. For example here, cyclohexene is given, 3-methyl cyclohexene is given, 3-methyl cyclohexene is given, N-bromosuccinimide is given, N-bromosuccinimide is given. Number of allylic carbons 2 here. This one is tertiary, this one is secondary. Which is more reactive? Tertiary is more reactive when compared to secondary. Which is replaced in this case? Tertiary hydrogen is replaced by incoming bromine. Incoming bromine here. So that means tertiary hydrogen undergoes allylic halogenation. Allylic halogenation. So bromine is here only. The He is replaced by bromine. He is replaced by bromine. In this space, if you take chlorine or bromine, N-bromosuccinimide, N-chlorosuccinimide, sulfur chloride compound in the presence of high temperature, then form the allylic halogenation product. Allylic halogenation product here. So, thank you. Tomorrow we will see remaining preparation methods.